This question is related to combustion in the engine, hopefully not in the fuel tanks, so we should immediately rule out answer A. The real question is whether the air-fuel ratio is based on weight or volume. The correct answer would be the ratio of mass of air to mass of fuel, but since we do most of our flying on Earth, we can substitute weight. Answer B is correct. Combustion is a chemical reaction involving the hydrocarbons in gasoline and the oxygen in the air. It looks something like this, where the fuel is a long string of hydrogen and carbon atoms. It reacts with oxygen atoms to give off energy, and has carbon dioxide and water as byproducts. The reaction requires a certain number of each kind of atom, and any extras are wasted. There's one perfect ratio where everything gets used up, and this is actually a ratio of number of molecules in each of fuel and air. Instead of counting the number of molecules, though, we can use mass, or weight, because a given number of atoms will weigh the same no matter the volume. So to reiterate, air-fuel ratio is the ratio of mass of air to mass of fuel, which is similar to saying weight. Combustion doesn't care about volume. Problems arrive when we apply this to small airplane engines, though, because the only tools available to the pilot affect volume, not mass. The throttle valve controls the volume of air that enters the carburetor, but it's the weight of the air, which is to say the number of molecules, that matters to combustion. As we climb to less dense air, the volume of air entering the engine stays the same, but the density and weight of it goes down, and the number of oxygen molecules goes down. The mixture knob controls the volume of fuel that is allowed to mix with that air, which has roughly the same weight and number of molecules, no matter the altitude. So as the airplane climbs, the fuel weight stays roughly the same and the air weight gets lighter and lighter, meaning the mixture is becoming unbalanced. There's too many of those hydrogen and carbon atoms for the decreased number of oxygen atoms. These hydrocarbon molecules are what we pay for at the fuel pump, and a bunch of them are now being flushed out the exhaust pipe because they couldn't find oxygen molecules to react with. Appropriately, this is called a rich mixture, and it does help with engine cooling, but to an excess, it's just wasteful. So the mixture control is adjusted to restore the desired ratio of air molecules to fuel molecules, or more simply, the ratio of air weight to fuel weight. That covers the important points, but here's some fine print. First, this chemical formula was for octane, which is just one component of the complex mixture of chemicals in avgas. This affects the actual ratio, but not the definition of air-fuel ratio. Second, there's more than just oxygen and air. In fact, it's mostly nitrogen. The mass of air, when air-fuel ratio is discussed, includes everything, not just oxygen. This also doesn't really matter to this question. The amount of oxygen in the atmosphere, around 23% by mass, doesn't change at different altitudes or pressures. Both air as a whole and oxygen specifically are less dense at high altitudes, so the difference cancels out. Finally, that ideal ratio where all the gasoline and all the air is used for combustion, called the stoichiometric mixture, is not necessarily the desired ratio for aviation engines. The hottest exhaust gas temperature, peak EGT, occurs at this ideal ratio. Some aircraft manuals call this spot best economy. A mixture slightly leaner or quite a bit richer may be preferred to balance power, engine health, cooling, smoothness, and economy.